Today we're going to talk some more about equivalence classes. In the last example, at the end of the last video, we had the example of schools, where we said we can take the whole world and divide it up into schools so that we say that one person is related to another person if they're at the same school as the other person. So here's the entire world, and there's this school and that school and that school and so on. And there are some people who aren't at school, of course, and so they're individual little dots all by themselves because they're not at school with anybody. Now what we did in this example is we started with some schools, and from that we made an equivalence relation that said A is related to B if and only if A is at school with B. Now, what we could have done if we were extremely strange, which of course we're not, is we could have just started with a list of all pairs of people in the world and who are at school with each other. So we just have a list of pairs of people who were at school with each other, and then we could stare at that list for a really long time and work out what all the schools were, even though we didn't start off knowing what all the schools were. So that would be quite a strange way of going about it, but that's in mathematics what happens if we start with an equivalence relation and we get from it the set of equivalence classes. And it just shows that if you try and do too many real-life examples for maths, it can start sounding a bit stupid. So the idea is that given an equivalence relation, of a set S, we can partition S into equivalence classes. So, for example, given some element, let's say A, in S, the equivalence class of A is all the elements of S that are equivalent to A under this equivalence relation. Okay, so given A in S, the equivalence class, and we often write it as A with square brackets around it, that's the equivalence class of A, is the set of all the elements of S, all elements of S, such that A is related to X under this equivalence relation. So it's the equivalence class because it's the class of all the things related to A. So in the case of this schools example, you would get exactly all the pupils in the same school as this person A. Okay? And in the case we had before of being siblings, you would get all the siblings, this class would contain all the siblings of this person A. So for example, e.g., this would be all people at school with A. So first of all, notice that the equivalence class of A might be the same as the equivalence class of B. For example, note that the equivalence class of A is actually the same as the equivalence class of B. Well, can you see when it's the same? This will be the same set for A and B, provided A is actually related to B. So this is true if and only if A is actually related to B under this equivalence relation. So given an equivalence relation which I'm calling tilde, these will be the same equivalence class if and only if. Right? So the school, you can think of this as the school that A goes to. Right? The school that A goes to is the same as the school that B goes to if and only if A and B are at school with each other. Okay, so that's basically saying the same thing, but it can be a bit confusing because these two things don't look like they're equal. Now, if you write down all the different equivalence classes, you get a nice partition of the set S. So what does that mean? It means that every element of the set is in precisely one of those classes. So that means that I split up this very nicely. There are no overlaps. Usually when you draw all the sets that things are in, you might get some overlaps, right? You might get things like this in the usual Venn diagram picture. But what I'm saying is that all those intersections are going to be completely empty. So this gives a partition. Here's a partition. Oh, that's what we just said. We can partition S into equivalence classes. So what that means, let's see, where on earth can I write it? It means that, actually I can get rid of this diagram, I don't need this diagram anymore. So it means two things. One, every element of S is in at least one equivalence class, well, precisely one equivalence class, i.e. every element of S is in exactly one equivalence class. So let's see if we can prove that. What would we have to do to prove that? Well, obviously, every element of S is in at least one equivalence class because it's in its own equivalence class. Okay? Now, is it possible for an element to be in two different equivalence classes? That's the question. Okay, so what I'm going to do is I'm going to move this definition up to the top so it's still there. The equivalence class of A is all X in S such that A is related to X. So we're going to claim that, well, there are lots of different ways of saying this. So we can claim that every element is in exactly one equivalence class. Every X is in, okay, I'm about to write exactly the same thing down again so I can rub that out. Every X is in exactly one equivalence class, which also is the same as saying that if X is in two different equivalence classes, well, actually they had to be the same equivalence class. So if X is in the equivalence class of A and X is in the equivalence class of B, then those two equivalence classes had to be equal. Okay? Well, let's prove that. Remember that they are the same equivalence class precisely if A and B are actually related to each other. Okay? Now, what does it mean for X to be in the equivalence class of A? X is in the equivalence class of A if and only if A is related to X, right? Now, what about X is in the equivalence class of B? X is in the equivalence class of B if and only if B is related to X. So if both are true, so if both are true, then, well, if A is related to X, then we also have that X is related to A, right? In fact, I should have done this the other way around. No, it's all right. So if both are true, then we have nearly run out of time. So we've got B is related to X and X is related to A, but by transitivity that means that B is related to A by transitivity. And so that implies that the equivalence class of B is equal to the equivalence class of A as required. I'm going to draw a box to show that I've finished.